Now that we have an idea of how everything comes together, and in fact we have a system that we can go ahead and run once the once the client framework even has some implementation in it, a system that we'll be able to run against the actual server. Now that we've done all that fun stuff, let's go ahead and actually get some stuff implemented in the client framework. So I'm going to go ahead and I'm going to start with the transport base. Remember, the transport base is going to be the object that's responsible for sending information to the server in the form of an operation code and a dictionary of byte and object. It's also responsible for receiving events, and when it receives those events, it'll dispatch them to the transport listeners. So again, this is where you would, this is the class that you would overload if you wanted to support a different transport mechanism, such as an in-memory transport or a different networking framework altogether, or maybe even your own networking framework. So let's go ahead and start, and I'm just going to run through this class from top to bottom. So first we have its private constructor, and the constructor is just going to instantiate its objects. Remember, we have our callbacks, so I'm going to instantiate those. We have our event handlers. I'm going to instantiate those. And because this is an array, we have to provide a max value, the size of the array. And what I'm going to do here is I'm going to use byte.maxValue. And that's because our event codes are effectively bytes, meaning we'll only ever be able to have 255 unique, or 256 if you include 0, unique event codes. And so we can safely contain all of those within a predefined array that is of has the size of byte.maxValue, which is going to be 255 elements. Actually, it's going to be byte.maxValue plus 1 because of 0. Yeah, there we go. Almost had a off by 1 error there. Then we're going to instantiate our listeners, so a new hash set. Next up, we're going to implement add event reader. So the way that I have our modules set up is they have this method that returns a IEnumerable of event reader module registrations. So what I'm going to do is I'm going to say for each var registration in event readers.get registrations, and then I'm going to do something. Now what I'm going to do is going to look a little weird, but what the purpose of what I'm about to do is basically we want to be able to register multiple times to the same event for whatever purposes we might have. And to facilitate that, I didn't want to make the event handlers be an array of lists of actions. I could have done that, but it's going to be it's not going to be very often that we're ever going to register more than one event. So what I'm going to do is I'm going to use a closure to support the ability, basically a closure and just method composition. It's a very functional concept, but it allows us to very cleanly allow multiple event handlers to be registered to the same event, and it also will not impact the performance of event handlers that only have one event handler attached to them, which is going to be 99.9% of all of our event handlers. So what I'm going to do here is I'm going to say if event handlers at cast2int registration.code, because we're indexing the array by the event code. If this does not equal null, then what I'm going to do, and this again is going to look a little funky, I'm going to go ahead and say, how am I going to do this? I'm going to say something like var old handler equals event handlers at int registration.code. Then I'm going to say event handlers at cast2int registration.code equals, and I'm going to create a lambda here, and I'm going to say code comma parameters goes into, and I'm going to open up a multi-line lambda, as you can see right here with the curly braces. Then I'm going to invoke old handler with code and parameters, and then I'm going to invoke registration.action code parameters. So you see what we're doing here is we're basically saying, okay, well, if we already have an event handler for this, we're going to set the thing that we're invoking, the action, the event handler, to a new method. And that new method is going to invoke the old handler, and then it's going to invoke the new handler. And the cool thing about this technique is it'll actually stack, meaning we could have 5, 6, 7 event handlers that all handle the same event. And we're basically going to be using just functional composition to do that, because we're creating a new function that invokes the old function and then invokes the other new function. And then that function becomes one function that invokes both those functions. And if we want to add another handler, we'll invoke the function that invokes both those other functions, and then we'll invoke the new function, and so on and so on, and it'll stack. It's a very interesting technique that I don't get the opportunity to use a whole lot, but like I said, it removes us from dealing with the complexity of having a list of event handlers, while still giving us the ability to have multiple event handlers without any additional performance hits. It won't happen very often, and this does actually make it impossible to unregister event handlers, but I'm fine with that. At the core level, event handlers are really framework-specific things. They're not like, because obviously you will have things like, you'll have transient systems like a select character screen that'll get added and then removed. That's fine, because that's handled by the next level of abstraction, the systems system. And the event handlers are more about what happens at the transport layer. And once they're registered, you can't unregister them. But that's fine. I don't see any need to do that. And if there ever is a need to do that, well, we can readdress how we add event readers. But that's just going to require a localized change to this class. Next up, I'm going to add an else clause to this if statement, and I'm going to say event handlers at int registration.code equals registration.action. So this is the simplest case. We found a registration, the code wasn't already taken, so we simply assign the delegate to the array at the proper index, and that's it. Oh, yes, yay for ReSharper. It says access to for each variable enclosure may have different behavior when compiled with different versions of compiler. I'm glad this warning is still here, because funny enough, this behavior was actually fixed in .NET 4.5, I believe? In C# version 5? No, it was fixed in C# version 5. The runtime has nothing to do with it. Point is, however, is we're not using C# version 5 with this code. This is client code. What's going to happen here is we're going to run into the whole fun little issue with us hoisting up a variable that will change over time. To fix it, it's actually pretty straightforward. Above, when we create that lambda, I'm going to alias out the registration action into a local variable. So I'm going to say var action equals registration.action. And then inside of here, instead of saying registration.action, I'm just going to invoke action. Now what this does is it prevents a bug, a potential bug, because we now have a locally scoped variable that we hoist, and that variable will not change over the duration of the execution of this loop, whereas the value of registration, if we were to hoist this into a lambda, the value would change during the duration of the loop. And that's it. That's our add event handlers. Yeah. So now we have send operation. So send operation is simply going to delegate to, remember the send operation internal method? That's really the only method that you have to actually give an implementation for when you write your own transport layer. So I'm just going to delegate to that. Pretty straightforward. I'm going to pass send operation, pass in code, and, or sorry, send operation internal, passing in code and parameters. That's it. Now we have a slightly more complex send operation. This is the one that expects a response. So to do this, I'm going to say parameters at byte, cast byte, operation parameter system invoke ID equals underscore callbacks dot register callback on response. So remember how we have this little callback cache that will return a byte when we, or a byte ID when we register a callback with it, and then we're able to invoke that callback again when we get that byte back? That's what we're doing right here. After this, I'm going to send operation internal just like what we did before. So I'm going to say send operation internal, passing in code and parameters. All right, now we have add listener. So add listener is going to simply do underscore listeners dot add listener. I'm actually going to change listeners here momentarily. Actually, we can go ahead and do that. I made a small mistake here, and the reason is our child listeners need to, or our child classes need to have an ability to reference this underscore listeners. So instead of making it private read-only, I'm going to make it protected read-only. And by making it protected read-only, I'm also going to change the naming convention, because when you have a protected field, the naming convention that I prefer is to use the same convention you would use with a public field or a public property, and that is going to be starting with an uppercase. So I'm going to change it to listeners. Of course, by doing that, I'm going to have to change the constructor. And then finally, going back down to the add listener method, I simply reference listeners instead of underscore listeners, but everything else changes or stays the same. All right, now we have to deal with our disconnect. We're not going to put anything in here. There's nothing to do. So yeah, now we go into handle system callback. So handle system callback is invoked when the child transport decides that there needs to be a callback operation on some sort of other operation. And to do that, pretty straightforward stuff. What I'm going to do here is for handle system callback, I'm going to say if code does not equal send system response, throw new argument exception, passing in something like code blank is not valid for handling system or handling responses, passing in code, and then passing in code as the parameter. So basically I'm just double checking to make sure that we're handling the right code. The reason I'm even passing in a code here is there might be a circumstance down the road where we might want to do something different depending on what operation code was sent in. Maybe we have a send system response, but then we have a different kind of send system response at some point. So I want to have that code still be handled at this layer, but I need to ensure that it's only going to be a send system response. Otherwise, I'll consider the response invalid. Then what I need to do is I need to get the invoke ID. I need to get the ID. Remember this ID that we set up here and we sent to the server? Well, I need to extract it from what the server sent back to us. So I'm going to say method invoke ID equals parameters at cast to byte operation parameter dot method system invoke ID. And then of course I also want to cast this to a byte because it will be a byte value. Then I'm going to say var callback equals callbacks dot get callback, passing in method invoke ID. And then I'm simply going to invoke callback, passing in code and parameters. So this is how we'll be able to get a response from a particular method invocation, or any sort of particular invocation that we might have. Now we have handle event. So what I'm going to do here is I'm going to say var handler equals event handlers at cast to int code. Actually, cast to byte code won't make a difference, potentially more performant. And then I'm going to say if handler equals null, then I'm just going to throw a new exception. Yeah, I think I'm going to start throwing a new exception. There may be a circumstance in the future where I might not want to throw an exception here. I might want to do something different. But for now, I'm going to throw an exception. And I'm going to say handler for event code blank was not registered. Again, I don't foresee a valid reason for us to be receiving an event that we don't have a handler for. So I'm going to default to throw an exception. And in the future, if I decide that there's a valid use case for this, I'll just have it early exit if there's no handler. But for now, we're going to throw an exception. Then all I have to do is invoke the handler, passing in the event code and the parameters. That's it. That is our client transport base. So basically, it's just a little, it's just a bunch of code that we can reuse for our transports, and nothing more, if we want to. There's nothing stopping us from making an iClient transport that doesn't inherit from client transport base. It's just a convenience class that gives us a lot of built-in functionality that we can reuse. And yeah. All right, let's go ahead and move on to our Photon transport. So coming over here, we're going to go to the Photon client transport. I want this to be implemented at the base level because Photon is the framework we're using. I'm not scared of referencing Photon from our assemblies. Of course, I want to make it possible for you not to have to use Photon, but because it's going to be used by virtually all of our clients anyway, I want this Photon client transport to exist within the client assembly. In addition, I'm also going to remove the status changed because we no longer need it. We now handle that through our listeners. The next thing I'm going to do is I'm actually going to go ahead and add a reference to log4net in the Buzz MMO client project. So I'm going to go to references. I'm going to say manage new. Oh, I don't want to manage NuGet packages. I want add reference, and I'm going to browse under the lib folder into Photon server and log4net. The reason I'm not using NuGet to get log4net is because I want to have the only version of log4net that we use be the one that Photon uses to prevent any sort of nasty assembly level incompatibilities that would result in having to do assembly redirects and all that fun stuff. Also, we're mixing and matching .NET 3.5 with .NET 4.5, and I don't want a different NuGet package level to break with referencing multiple versions of the same assembly. So basically, yeah, we're just going to be using the one that comes with Photon. And then I'm going to say, up at the top, I'm going to say private static read-only ilog, and I'm going to bring in log4net. I'm going to say log equals log manager get logger type of Photon client transport. All right, now let's work on the constructor. The constructor is going to do nothing more than instantiate the peer. So I'm going to say new Photon peer. I'm going to pass in myself as the Photon listener, and I'm going to pass in a connection protocol of UDP, because that's what we're going to be using for now. I might switch over to TCP in the future, but I'm only going to do that once we have some benchmarks in place that we can measure the differences. The connect method, pretty straightforward. It simply defers to the peer. So I'm going to say peer.connect server address application. That's it. Disconnect. It'll give us a warning right now, and that's because the client transport base has an implementation, but it's virtual. What I'm going to do here is I'm going to overwrite it so that we no longer get that that warning. You have to do that. You have to make sure you overwrite it, otherwise things will not work in the way you expect them to. Then I'm going to say peer.disconnect. Service, peer.service. So as you see, these methods that we're exposing are just delegating down into the peer, and that's it. Now we have send operation internal, which is really, this method is where all the operations from our entire client go through. And all it's going to do is say peer.opCustom. We're going to cast to byte the operation code. We're going to send in our parameters, and then we're always going to send reliable. The client should always send reliable to the server, but there are circumstances where the server might not want to send reliable to the client. All right, now we have onEvent, which is pretty easy to handle because we have the handle event method. Remember the handle event method that's on the base type? Well, we can just delegate straight into that. And what I'm going to do is I'm going to say cast to event code, event data.code, and then event data.parameters. That's it. On operation response, I'm going to say handle system callback, cast to operation code, operation response to operation code, then operation response dot parameters. That's it. Again, all just delegating into either the base type or our peer. Now we have debug return. Debug return, I'm going to say log.debug format, and I'm going to say debug return placeholder, and then I'm going to say, or placeholder, and I'm passing level and message. Actually, I can format this maybe a little bit different. Yeah, that looks fine. All right, then we have on status changed. I'm going to say log.debug format, status changed placeholder, passing in status changed. Then what I'm going to do is I'm going to notify all the listeners that the status has changed to something. So I'm going to say var connected, or sorry, I'm going to say var status or var transport status equals status code equals connect question mark client transport status dot connected, otherwise client transport status dot disconnected. Then I'm going to say for each var listener in in listeners, which is that protected field that we have, this listeners. Then I'm going to say listener dot transport status updated transport status. And that's it. So not a whole lot going on in our Photon client transport. It just glues together Photon into the framework, which is exactly what it's supposed to do. It's just glue. All right, so we've implemented that. We've implemented that. We've gotten that. We have that. We have that, and we have that. So that pretty much gets us done with our infrastructure namespace. So now let's go ahead and move on into our client systems. I want to go ahead and implement the client systems because this is the big one. The first thing I'm going to do is I'm going to add a NuGet reference to castle.core. So I'm going to go up to Solution Explorer. I'm going to right-click References, go to Manage NuGet Packages. I remember before NuGet, it was very, very, very dark time. I can just remember all the depends. It was just terrible. So now we have castle.core, which we'll want to install. I can't believe even people were C# developers back then. It was so terrible. And now that we've imported it, we can go ahead and import the castle.dynamic proxy namespace up at the top of the file. All right, so now let's just work our way from the top to the bottom. Again, this is the big one. This is the biggest class that we're going to have to implement, and it's not too scary. Let's start off with the constructor. The constructor is just going to alias out our different component stuff. So component map equals component map, factory equals system factory. Then we'll need to do our operation writer equals operation writer. Then we need to instantiate our concrete type to info as a new dictionary of type and system information. And then we also need to instantiate our systems by interface ID, which I'm going to instantiate to a new array of iSystem base, passing in byte.maxValue plus 1 as its size. Now we have create. So how do we create a system? Well, the first thing I want to do is ensure that the system hasn't already been created. So I'm going to say if systems by interface ID at interface component type.id does not equal null, then throw new argument exception system with interface type placeholder has already been created. And then I'll do interface component type.full name. And then I'm also going to add the param name as interface component type. Then I'm going to say type concrete type. This will make sense in a second. Then I'm going to say systems. Well, actually, before I do concrete type, I'm going to do operation writer.create system interface component type. I'll talk about that in a second as well. And then I'm going to create concrete type. Then I'm going to say var system instance equals _factory dot create system. We're going to pass in the interface component type dot type as the type to create. We're going to pass in create proxy for as the proxy factory. And then we're going to pass in out concrete type as the resulting concrete type. Then I'm going to say _concrete type to info dot add, passing in the concrete type that we got, and passing in a new instantiation of system information, passing in the interface component type and the system instance. Then the final thing I'm going to do is I'm going to say systems by interface ID at interface component type.id equals system instance. let's see here. Actually, you know what a better way to do this would be? Better way to do this would be to, instead of having an array of iSystem bases, why don't we have an array of system informations? And then so I'm changing the array up here of systems by interface ID to returning system information. And then I have to change the constructor to instantiate a new system information. Then, instead of adding this directly, I'm going to take this, I'm going to cut it out, and I'm going to say var system information equals, and I'm going to instantiate it here as a local variable. Then I'm going to pass it into the add method, and then I'm going to add it into the systems by interface ID array. I think that should work a little bit better. You'll see why when we get to the destroy method, but that removes a little bit of a kludge I had to do previously when I wrote this out. Anyway, let's just go by this method line by line. We first of all make sure that the system hasn't already been instantiated. If it has, we throw an exception. Then we do operation writer.create system. What does this do? The funny thing is, it won't do anything at all. I put this code in here as in preparation of us being able to share this client systems class with the server. Because like I said earlier when we started talking about the client framework, the more I started to work on this, the more I realized we could share a lot of the same code between the server and the client. They don't have to be so different from each other. And part of that was came into play when I designed this class, and I decided, you know what, just as a preemptive measure, I'm going to allow the systems operation writer to be notified when a system has been created, so that when we plug this into the server, we will be able to add in an implementation of create systems and use it to tell the client to instantiate its proper system. In the client, nothing will happen, but it could be useful once, or will be useful once we move it into the server assembly as well. Next up, we need our concrete type local variable because we're going to be stuffing it with whatever concrete type was returned by the factory. Next up, we instantiate our system by telling the factory to create a system based on the client interface type. We also pass in the factory for creating a proxy for the server type, and then we extract out the resulting concrete type out of the factory. Then we instantiate our system information, which this is just a way to contain the interface component type and the instance of the system. Then we have two ways of accessing our systems. We can access our systems through concrete types or by interface IDs. So we use two separate data structures to facilitate that. That's it. Create proxy for is going to be pretty straightforward, very similar to what we have on the server. I'm going to say return component proxy generator dot create interface proxy without target. I'm going to pass in other interface component type as the first parameter. For the second parameter, I'm going to instantiate a new proxy interceptor. And then I'm going to pass in component map dot get component other interface component type as the mapped component. As the operation writer, I'm going to pass in operation writer. So remember, this, oh my god, that's ugly. Stop it. There you go. Remember, this proxy is responsible for being the interface that we use to communicate from the client to the server. So it needs to have a proxy interceptor. The proxy interceptor needs to have an operation writer for one, so it can send data to the server. And then it also needs to know more information about the actual component itself. So we use the component map to acquire that information. All right, let's move down to destroy. Destroy just removes a system, not too crazily complex. We're going to put in a sanity check at first. I'm going to say if systems by interface ID at interface component.id does not equal, or sorry, equals null, then throw new argument exception. System with interface type placeholder is not created. And then I'm going to fill in that placeholder with interface component.type.fullname. And then as the second parameter, or second argument, sorry, to the argument exception, I'm going to pass in the interface component string to define which parameter we're referring to. Then I'm going to extract the system. It's going to be the first thing I'm going to do. So I'm going to extract the system by accessing systems by interface ID at interface component.id. Then I'm going to say system.systeminstance.dispose. Because remember, we're now working with system informations, not with concrete systems. So we have to access that by going to system instance. Then I'm going to say operation writer dot destroy system interface component. Then I'm going to say systems by interface ID at interface component.id is going to be set to null. Then I'm going to say concrete type to info dot remove, and I'm going to say system dot concrete type, which hasn't been created yet. We're going to create a property on system information to know what the concrete type is so that we can remove the system information from there. All right? So we'll fix that later after we get through all these methods. Now let's do get by interface ID. Pretty straightforward. Return system by interface ID at interface ID dot system instance. Not that hard. Now we have our get by concrete type. Our get by concrete type is going to simply say return concrete type to info at type of tconcrete type dot system instance, and we have to make sure we cast this return value to tconcrete type. Then we have a try get. So the try get is going to say system information. I'm going to say if not concrete type to info try get value type of tconcrete type out information, then set value to null and return false. Otherwise, return or set value to cast to tconcrete type information.systeminstance return true. So it's a basic try get implementation that we basically just delegate into our concrete type dictionary to do. Now let's do our contains. Contains will simply return concrete type to info dot contains key type of tconcrete type, and that's it. We could also add the same, maybe I overlooked this. I should add the same generic type constraints. So I should say where tconcrete type is a class and implements iSystem base. Just as a nice little syntactical sanity check. All right, now we have dispose. So what's dispose going to do? Well, it's just going to blow itself up. We're just going to dispose all of our systems and reset everything back. So to dispose all of our systems, we could loop through all of our systems and invoke destroy, or I guess there's a bunch of ways to do this. I'm just going to say for each of our system in concrete type info system.value.systeminstance.dispose for one. Then I'm going to say concrete type to info.clear. Then I'm going to say for var I equals 0, I smaller than system by interface to ID dot, or sorry, system interface ID dot length I plus plus system interface ID at I equals null. Actually, I'm going to go up here, and after we dispose the system, I'm going to say operation writer dot destroy system value interface type, and that works good. So yeah, that's our dispose. We just clear out all of our stuff and we dispose all our systems. Okay, so now let's do our proxy interceptor first, which I misspelled intercept. Derp. So our proxy interceptor, the intercept method invoked anytime anybody invokes a method on the system proxy. We're simply going to say var method equals underscore proxy interface component dot get method invocation method, and then I'm going to say system or operation writer dot invoke method, passing in our method. Ooh, this is actually going to be a to-do. Yeah. Hold. Yeah, we're gonna have to wait a little bit to do this one. The reason we need this is I overlooked us actually writing the RPC response classes. They're actually going to be really small, but we're going to have to write them later because I kind of want to get through all this other stuff. For now, what I'm going to do is I'm going to say operation writer dot invoke method, passing in method and invocation dot arguments. So basically what I'm doing here is I'm just ignoring whatever response happens. But in the future, we will go ahead and write our RPC response classes, and then we'll fill in this blank spot right here. Okay, the last thing that we need to do is we need to pass in the concrete type into the system information when we instantiate a system. So I'm going to add a new parameter to its constructor, and it's going to be type concrete type. We're going to add a new public type concrete type get private set as a property, and then we're going to set concrete type to concrete type. That's it. Now we have one more error, and that's going to be on our create method. Because we changed the constructor of our system information, we now have to go in here and actually pass in concrete type in there. But that's fine. Either way, although this is the biggest, one of the biggest classes that we've written, it's not that complicated if you just break things down line by line and try to figure out what's going on here. The client systems is nothing more than a bag of systems. The real work is going to be done in the system factory, which we'll deal with. All right, so let's move on to the systems operation writer. We haven't done this yet. So let's go up here to Solution Explorer and go to our systems operation writer, which is responsible for invoking things on the server. Its constructor is going to be pretty straightforward. We're just going to set serializer to serializer and transport to transport. Not a whole lot to say about that. We have our invoke methods. So our invoke methods are going to look very similar to the way our invoke methods worked on the server. I'm going to say var parameters equals new dictionary byte object. I'm going to say set parameters method arguments. And then I'm going to say underscore transport send operation, and we're going to have to pass in our operation code. And in this case, the operation code is the ID of the component, which is something I actually might change. I'm not sure if I'm liking that so much, but for now we'll stick with it. I'm going to say operation code method.component.id, and the parameters are simply going to be parameters, and that's it. Now we have our second invoke method, which expects a response, but the first part of the method looks pretty much the same. Var parameters equals new dictionary byte object, set parameters method arguments, and then we're going to do transport send operation. We're going to pass in cast to operation code method.componentID parameters. Then we're also going to do parse response, and we're going to invoke parse response and capture the onResponse method or onResponse parameter. We'll talk about parse response here actually right about now, because create system and destroy system are going to remain blank. So parse response, maybe one of the first times you guys have seen a method return a delegate like this. Basically what we need to do is parse response you can think of as the shim between the way the transport sends our response and the way we want our client systems to receive our response. We want to actually perform the deserialization of the response right here. Because remember, our transport has this overload that takes in a callback that the callback will be sent back to us once the server responds to that particular message, right? Well, we need to actually translate the way that the callback from the transport layer works into the way that we want it to work. We're basically upping the level of abstraction here. And there's a very specific reason why I don't want this at the transport layer. I don't want the transport layer to deal with deserializing the IRPC response. For one, when we go to a different kind of transport, it's very unlikely that we're going to change the way IRPC responses are deserialized. And so I want to be able to carry over that implementation with me. Second, there could be very easily more than one case with the server that we would expect a response that has nothing to do with the systems. So I don't want to hard code the concept of our systems framework into the transport layer, because that really ties our hands with a variety of other things that we could potentially do. So I want the transport to be kind of low level per se, where it just understands things like operation codes and untyped dictionaries. Then I want this class to be responsible for translating that low level stuff into something that the rest of the system can consume. So we need to send a delegate into this argument. We need to send some sort of callback. But we need that callback to also have a reference to onResponse. Now I could have done a multi-line lambda here and hoisted the onResponse parameter. That would have worked just fine. But I kind of wanted to show you guys an instance where if you're worried about a multi-line lambda becoming too long and impacting the readability of your method, this is how you would effectively break a multi-line lambda out into a method to increase readability by having your code be in a different method and not clutter your existing method. You would write a method that returned this, a delegate. Funny enough, what we're going to be doing here is going to be interesting. I'm going to say return, and it's going to return a lambda. So return code comma parameters goes into multi-line lambda. So again, this is how we can take this code that we would have had to write up here and instead dump it down here. Okay, so parse response, how are we going to do this? Well, parse response is going to basically be the opposite of how the client context works. So basically, parse response is the opposite of what this is right here. So we need to extract out response is valid, extract out operation errors, and we need to deserialize the result if it has one. Okay, so here's what we're going to do. We're just going to alias these things out. We're going to perform the deserialization, and we're going to worry about instantiating the IRPC response later, because we don't have concrete IRPC responses yet. So I'm going to say var is valid equals parameters at byte operation parameter dot response is valid. Var operation errors equals parameters at byte operation parameter dot operation errors, and then I'm going to launch into an if statement. I'm going to say if parameters dot contains key cast to byte operation parameter dot result bytes, then do one thing, otherwise do another thing. Now here's where things get tricky. I don't know what the type is because I don't know what the method is. Nor do I know what the component ID is. I might have overlooked something here. There's no way to deserialize this unless we know what the method is that we're expecting. Actually, we do know what that is. I can just add a different... yeah, sorry about that. Crisis averted. Okay, so coming back up here to this invoke method implementation, the one that takes in the callback. When it invokes parse response, I'm going to send, in addition to onResponse, I'm going to send in the method that was invoked so we can get additional information about the method. Now back to the parse response, the first thing we're going to have to do is we're going to have to take in a mat method. And then what I'm going to do is, instead of putting this having this if statement predicate on whether or not the parameters contains a result bytes key, I'm going to say if method dot return type equals response with result, then do something. Otherwise, do something else. Actually, I'm going to say else if method return type equals response, then do something else. Else, throw new invalid operation exception. Cannot accept return for method without return value. It's going to be method dot method info dot name. Or actually, we're going to do placeholder 0, placeholder 1. We're going to do method dot method info dot declaring type dot full name. So just to break this out a little bit, this is our full error. If somehow you're trying to invoke a method on a method info that doesn't return anything and we get a return back, that's obviously a bug. So let's go ahead and throw an exception out there. Okay, so if return type is response with result, I'm going to say var result bytes equals parameters at cast a byte operation parameter dot result bytes, and I'm going to cast this into byte. Then I'm going to say var result object, or sorry, I'm going to say object result object. And I'm going to say var using var ms equals new memory stream using var, or I'm going to pass in, of course, result bytes into the memory stream. Then I'm going to say using var br equals new binary reader, passing in ms as the underlying stream. Then I'm going to say result object equals serializer dot read object, passing in the reader, and then passing in method dot return type, or result type. And that's it. Now, to do, create new RPC response object and invoke on response. And that's that. So that's how we parse responses. Okay, so we're gonna wait on until we have an implementation of IRPC response before we implement these. All right, now let's look at set parameters. Set parameters gonna be pretty straightforward. We've seen it before in the server. I'm gonna say var argument bytes using var ms equals new memory stream using var dw equals new binary writer, passing in ms as the underlying stream. I'm going to say serializer dot write arguments, passing in the binary writer, passing in method dot parameter types as the types, and passing in arguments as the arguments. And then I'm going to say argument bytes equals ms dot toArray. Then I'm going to say parameters at byte operation parameter dot argument bytes equals argument bytes. I'm going to say parameters at byte operation parameter dot method ID equals method dot ID. And that's it. That is our systems operation writer. All right, so now that we've done that, let's go ahead and move on to our activator system factory. So opening up our Solution Explorer, I'm going to scroll up to our most basic system factory, which is our activator system factory, and go ahead and write it out. So the constructor is going to be pretty straightforward. System type registry equals system type registry, init system equals init system. This, of course, will fail because I forgot to add the object parameter to our init system delegate. So let's go ahead and do that. All right, now that we've done that, let's go ahead and create our system. What's the first step? Well, the first step is to establish what concrete type we need to instantiate for this interface type, that's where we use the system type registry. So I'm going to say var registered system equals system type registry dot get system from, and I'm going to do get system from client interface type. Then I'm going to instantiate the system. So I'm going to say var system instance equals cast to iSystem base activator dot create instance, passing in our registered system dot concrete type. So we look up the system in our type registry, and we use that information to instantiate an instance of the appropriate concrete type. Then I'm going to say init system, or sorry, I'm going to say var proxy equals proxy factory, and I'm going to pass in registered system dot server interface type, because that's the proxy that we want to create. Then I want to say underscore init system, and I want to pass in a cast to tsystem base system instance, as well as the proxy. And then I'm going to simply just say concrete type equals registered system dot concrete type, and then return system instance. So that's it. 6 lines of code. So again, first we establish, because all the system factory knows about is the client interface type that we need to instantiate. First thing is we get the registered system. Then we instantiate it. Then we create the proxy. Then we initialize the system with the user-defined initialization logic, passing in the system instance as well as the proxy. Then we tell the systems, the client systems class, what concrete type we ended up using, and then we return the instance of the system we created. That's it. So let's go ahead and move on to our systems event reader. So our systems event reader, going to be pretty straightforward. All it does is delegate into the actual systems. So we have our serializer and our systems. We're just going to set those to our local fields. Serializer equals serializer, systems equals systems. Then we have our get registration. So our get registration, its sole responsibility is to inform the transport of all the callbacks that we support on this. We could have done this with some fancy reflection, but I opted to go with something like this. It's pretty straightforward. It's not that scary. Basically, there's a couple ways to do this. I can return a new array. I think that's what I'm going to do. I'm going to say return new array. And I'm going to say new event reader module registration, event code dot add system event. Actually, I'm going to do this in order. So the first one is event code dot invoke method on system, invoke method on system event. Then we want to instantiate event code dot remove system event. Then we want to instantiate another one, event code dot sync systems component map and sync systems component map event. Really, that's it. So it just returns a map, basically, of what events we handle. Notice how I did make a conscious decision to pass in the event code into the event handlers themselves. The reason I did that is because of the possibility of one method actually handling multiple events, and we'll need a way to distinguish the event code in the case of that happening. Alright, let's start with the most difficult to implement one first, and that is the invoke method on system event. So this means the server told us to invoke a method on one of our systems. The first thing I'm going to do is extract out the client interface. So I'm going to say client interface equals underscore systems dot component map get dot components at, this is going to be fun, at byte cast a byte parameters at cast a byte event code parameter dot client interface type ID. So that's the first thing we do. We extract the client interface. Next up, we extract the method. So method equals client interface dot methods at cast a byte parameters at castabyte event code parameter dot method ID. So we extract the interface and we extract the method. Now we have to deserialize the arguments. So I'm going to say object arguments var argument bytes equals cast to byte array parameters at cast to byte event code parameter, and I'm going to say argument bytes. Then I'm going to say var using var ms equals new memory stream argument bytes using var br equals new binary reader, passing in ms, and then I'm going to say arguments equals serializer dot read arguments, passing in our binary reader and our method dot parameter types. Next up, we get our system. Remember, we need our system object to invoke a method on it. So I'm going to say system equals systems dot get by interface ID, passing in client interface dot ID. Then I'm going to say method invoke, passing in system as the thing to invoke on and the arguments as the things to invoke with. And that's it. Now let's move on to add system event. Add system event is simply going to do similar things for the first line anyway. Client interface. Actually, I rarely do this, but I'm just going to copy and paste this. I can't. There we go. Just copy and paste this line from invoke on method on system event because it's the same thing. We need to get our client, we need to extract our client interface ID, and we need to get it out of the components array. So just copy and paste that line, and yeah. Like I said, I really do try to type everything out. I really try to avoid copying and pasting, but I wasn't going to write that line out again, especially because we need it exactly how it is. Okay, then I'm going to say systems.create, and I'm going to pass in client interface. For remove system event, I'm going to say systems.destroy, and I'm going to pass in client interface. Okay, sync systems component map. First thing I'm going to do is I'm going to say var formatter equals new component map binary formatter. I'm going to say var bytes, or how about var component map bytes equals cast to byte array, parameters at cast to byte, event code parameter dot component map bytes. Say var using ms equals new memory stream, passing in our component map bytes. Then I'm going to say var br equals new binary reader, passing in ms. And then I'm going to say formatter dot load, passing in our binary reader, and then passing in systems dot component map to synchronize the component map with whatever was set. And that's it. So that is literally going to be our client. I'm pretty sure, anyway. Blah, 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 blah. Yeah, that's our client. Okay, so we have our client transport base, and we have our status, and we have our module registration, and we have our transport, and I'm pretty sure all of this is good to go. Okay, so I guess we can go ahead and see if it works. Sure. Let's go ahead and try to launch Photon. I'm going to go ahead into my configuration manager, and I want to ensure that I have my server master and server region set to debug Nelson. Then I'm going to hit F6 to do a build all. Then I'm going to navigate into my Photon folder and remind myself which port the UDP listener is on. Pretty sure it's 5055, but I could be wrong. Port is... just give me a sec. photonserver.config. Port is going to be 5055, so I was right. Okay, so now I'm going to go ahead and open up the logs. Now that we have our logs open, We do see that Photon did decide to die in a fire there, as you can see by it not having started. Or did I not tell it to start? Right-click default start. Open up my log folder. Get my Photon CLR log, my Photon default log. Then I'm going to open up my server and master logs. I'm going to make sure it's going to be running. Service is running. Okay. Then we go to our console and we right-click references, or what? We right-click the project, say set a startup project, hit F5. Oh, it connected. Let's see if I got any exceptions over here. Doesn't look like it. Let's see if we open up our client context. Let's see if this ever happened. Yep. 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 Okay. So now what I want to see is if the login system was ever created. So what I'm going to do is I'm going to say protected override awake. I'm going to say log.info format, or how about info, created login system. And look at that. Okay, let's do a little bit more of an interesting test here. I'm going to open up base components system login system. And on basic test and basic client test, I'm going to change its parameter to int count. And on basic client test, I'm going to say int count. Then what I'm going to do is I'm going to open up the server, or sorry, the server master, open up systems, go into my login system, and obviously I'm going to have to change the parameter here to int count. Then I'm going to say if count is less than 100, then proxy.basicClientTest count plus 1. Then I'm going to go into my login system on the client, change its basic client test to int count, and then I'm going to say got test showing the count. I'm going to say proxy.basicTest count plus 1. Let's see what happens. Object reference not set to an instance of an object. Method info is null. Byte ID is 0. This isn't good. Handle event. Sync systems component map. Good. That's okay, method info is null. Component type is iLogin system server. Oh, you know what's wrong with that? I forgot to hit F6. What happened is that the server was using the old version of the component type. The old, remember how I changed the signature? Well, yeah, that wasn't going to work. Okay, now let's hit F5. And we don't get any messages. Actually, because we never started the whole loop. Because remember, I'm making kind of this loop where it'll ping back and forth until it hits 100. Well, we need someone to start the loop. I'm going to start that on the... I'm going to start it on the server. So I'm going to say protected void awake, or protected override awake. And I'm going to say proxy.basicClientTest starting with 0. I'm going to hit F5. And I forgot to hit F6 to recompile the server. Of course I did, because I'll always do that. And look at that. Let's one-up this and actually perform the same logging on the server as well as the client. So in the login system on the server, I'm going to say protected or private static read-only ilog log equals log manager get logger type of login system. And then on basic test, I'm going to say log.info format got count placeholder count. Recompile. Then let's watch the log as this happens. So on the master server right here, let's go ahead and hit F5. And I saw nothing. Why did I see nothing? Is my log4net config not? Oh, I never configured logging on the server. You know what? We're going to do that later. We're going to do that in another video. For now, I think that's pretty cool. This proves that we were able to send something from the server to the client and send something from the client to the server. And also showed how to go ahead and just change your component definition a little bit, update the code on the client and the server and all that fun stuff. And with the client framework in place, for the most part at least, actually using it, pretty straightforward. Just instantiate a couple objects, wire some things together, and then connect. So I think that about wraps things up, and we'll see you guys in the next video.